All right. Salutations, friends. Welcome to another episode of For Your Reference. I'm joined here with my friend Noah. This is the web series where we talk about the Rust programming language. Particularly, this is a series that's aimed at Rust beginners. So you might be some practitioner, you've been working in the industry for a few years, or maybe you're just an amateur programmer, but you want to learn more about the Rust programming language. This is the video series for you. In this episode, we're going to be taking a look at traits. And so this is actually something that we've talked about a number of times, sort of offhandedly throughout the series up to this point. We've used a bunch of them, but we haven't really quite explained, where they come from, what they are, how to use them, how to create your own, how to implement them for your own types, etc. Essentially, this idea is, oftentimes in programming, we have some types of functionality that can be offered are available to many types, right? So a good example might be like, we have lots of types that can be, stringified or encoded or displayed or whatever. And we want some way to sort of codify that in the programming language. So traits are the way, the idiomatic way in the Rust programming language to do this. And so this episode should just kind of tee you up. You're going to be dealing with traits all over the standard library. This episode is really for just to show you exactly how these things work, the syntax for it, etc., and how to do it for your own types. So anyway, Noah's going to be driving this episode. How are you, Noah?
Good. How are you, Eric?
I'm hanging in there, man. It's been a hot minute since our last episode. We were on vacation and whatnot.
Yeah. Well, I'm glad to be back doing it again. So
yeah, fantastic.
This is a topic that I think something I've used a fair amount. My Swift when I was doing more Swift work, but
so that would be Swift protocols.
Yeah, and Swift is protocols, I guess, but a lot of similarities actually. So if you're coming from Swift, you'll probably see that. But kind of stopped using it a little bit just because kind of felt like more work than it might have been worth all the time. But still good to know, and I think also we'll see a lot of the common traits that appear in Rust that are useful to know.
Yeah. I think you're right. I think a lot of programmers they actually kind of stay away from traits or this kind of polymorphic generic programming because like it kind of makes code very abstract, right? So you sometimes just talk about abstract concepts that your data is doing rather than the data itself, and some people don't like that, and there's certainly some trade-off there. So I feel roughly the same way. I try not to overuse traits myself. I think they're sort of nicely sprinkled throughout, but not overused, right?
Totally. Cool.
All right,
get into it.
Absolutely.
All right. So kind of broke this up into two different parts. In the first part, we'll go through kind of how to make your own traits. So this gives you a sense of the syntax to use, and then also how to implement those traits with a struct. And then we'll go into kind of as I said before, the common or the traits that you see a lot in Rust. And so those will be helpful for you if you were basically maybe you see an error when you're writing some code, and it might help to explain that error, or you might, just really just good to know how to use these so you can kind of be more of a functional Rust programmer. So, so the first one we're going to go through is just the kind of basic trait that I made up called summary. The summary trait just has one function or method on it called summarize. And that returns a string. So you can imagine it's kind of similar to like a toString kind of interface. And so what we're going to do is we'll have like this person struct, which should be a familiar syntax. And then this is new though, where we'll actually implement summary for that person. So the trait's up here, and then we're implementing it, and we basically fill in the method that we specified above. So we're just kind of, this kind of trait is like our way of kind of grouping a bunch of functionalities. So we're saying anything that implements summary is now going to implement this summarize function, and you'll see it here. And So you can actually call that. And then if we look down below at this, I've instantiated a person, and now I'm able to call summarize on it. And so that's pretty cool. And basically, you can expect anything that implements it this way, you can make that call. And you can see that that actually works. If we do quick run here in the terminal, should compile, and you can see that Eric gets printed out. I printed out a bunch of stuff here, but just look at that first line.
Hello.
So yeah, I mean, that's kind of a example of a trait, and then kind of how you implement it. The next part here, we'll look at another trait. So this one's a little more complicated. Not really actually that complicated, but just to show you how you can also provide like a default implementation in a trait. What that means is anything that implements that trait now will have an automatic implementation. So I won't have to, if it's always the same thing and I want all these types or these structs to have the same implementation, I can, and you can see that below. So I've made a struct called pangolin, and then I can just, I still have to implement it, but I don't have to do anything. And then if I look down below here, I automatically get that call. Rust is happy with that because it knows that this is an animal type, so it should have that method. And then it also knows that it has that default, where did I go? Sorry. It has that default implementation. So, and you can see that when I call it, I get derpy derp.
By the way, I absolutely love this default implementation. Animals definitely derpy derp by default.
And yeah, so that's kind of the default implementation syntax there. You can also still override that, and you can see that with the cow, we actually we get our custom override for that, for make noise. All right, so that's basically default implementations. Moving on, then we could see kind of a cool thing, and this was I thought this was useful in Swift as well. If you wanted to kind of add things to your type or to an existing type, in this case, I'm implementing summary for the I32 type, which is a built-in type, and I'm just having it say, you know, that I'm an I32 when I call summarize. So I can call. I've just declared an int here, right? And I can call summarize on it. And I think we were talking about this earlier, but a lot of like third-party libraries, they might do this sort of thing where they they might add some new functionality and they implement it for a lot of the built-in types. So you don't have to do that basically. And if you make custom types, you can do it too, because the trait's there, but that can be useful in that situation. If we look here, we can see that that actually works. Cool. All right. So the next part's a little more complicated, but and kind of getting a little bit more under the sheets of how this works in certain cases. So when we consume a type, we can use this kind of generic syntax. This probably will look familiar with, if you look at other languages, it's not that far off. In this case, we're saying this function can take any kind of animal trait type, and it's just going to call that make noise function on it. When you do this sort of thing, though, so here's an example where we've got our animal types here and here, up here, and we're passing them into this function down here. So Rust is actually going to generate two different make noise functions for each of those different types, since they are technically different. And this is what we call, I believe, type erasure. So we're essentially now we have like two different animal noise functions that take two different types in the end. And that's what we would also refer to as static dispatch. So this is if you ever look up kind of when you're looking around learning about traits, one of the things I think the article was talking about, it's like a no overhead abstraction. So you don't pay that cost to get the to figure out what method to call. Whereas in other languages, you might have this like a little bit of overhead for these kinds of generic methods, where it would have to look up the actual make noise. In this case, it's like an inline call directly. So this is kind of goes into that whole idea of Rust being very performant, or creating very performant code. But that doesn't limit you. In some cases, it may be necessary to do that kind of more dynamic like lookup. And in this case, I've kind of made this kind of strange type, but kind of like a collection of animals, the menagerie. And this is a vector of this box type, which holds animal types. So what that is really a vector of pointers to animals. And in this case, you'd end up with that kind of lookup. So you still possible to do that. And you could, if you think about it, this actually makes sense, because when you have this vector, you'd probably want things of all the same size. Whereas if it's just a trait, you don't know what the actual type is. So it might be different sizes, may have different fields in it. So, you couldn't necessarily, you couldn't handle that with this sort of static dispatch. So you could still, it's still possible. This Dyn syntax, I believe, is relatively new. But so if we take it away, actually, and if we recompile, you'll get a warning about that. This is just more about being explicit, I believe, so that we're like aware that we're dealing with a pointer rather than the actual type there, or the value. And so down here we're just calling that twice with each different type, and you can see that it still works down here. So we get the derpy derp, and then the custom Darius scary. I don't know, Eric, you want to add anything there, or kind of?
No, I think you summarized it quite well. I think that I think that if you're familiar with Rust or Swift protocols, or Java interfaces, maybe even Go interfaces or Haskell type classes, this is all pretty standard stuff for you. You've seen this kind of thing before, and I remember when I was very, very young, I was like, why would anybody ever use these interface things? Like, what are they for? And they're just so that you can write very abstract functions like you did make animal noise, where you don't necessarily talk about particular kinds of animals. You just talk about, I want to do some operation using like something that is an animal, right? And so you get sort of highly reusable generic code at the cost of abstractness and potentially like loss of sort of granularity, right? Mental granularity. And I also love that you pointed out that Rust does, of course, is trying its hardest to give you very performant code. So it tries to, in the sort of default case, give you the highest performing code, right? And you only elect to explicitly take a slower approach with more overhead, right?
Right. Cool. All right. So now that we've kind of gone through how to create a trait and default implementations, as well as just how you implement a trait for an existing type, and now we're going to kind of go into basically these common traits that you see all over Rust. And yeah, I've just kind of started with some simple ones, and we'll go through basically what they do and how you use them, and probably where you see them. So the first one, probably actually maybe actually less common. We realized after we wrote this, but it kind of builds on to the next one. So this one's just called toString. This is actually kind of similar to the summarize one we made before. But this is kind of a building block to get to display, which we'll talk about next. But essentially, this one just lets you turn your object into a string, and you can see it's already implemented for a lot of things, and that's partially because a lot of things implement display already. And so, basically, to implement display, you have to implement toString, and so that's why it's kind of a building block here. And I think that's pretty straightforward, and we'll run this one too for the hell of it. You can see you get that I like 5. So that is pretty good. The next one though, display, is like a little more interesting. Again, this is used for essentially. I think we've actually used this in other episodes, maybe, or at least touched on it. But you can use this to format your value or your object into a string. And in the string, if you just put that little open curly brace, close curly brace, you'll be able to see your object. By implementing this, you'll be able to use it in that kind of fashion, and you can see it here. It's being used. So instead of actually calling that, here I'm calling toString, and because string implements display, this works here. But here I'm since I has already implemented display, I can just call print line with that directly, and it will work. And you can see that here. I like to display 5. Cool. All right. In kind of the same vein, you can see the debug trait as well. And we've definitely seen this. This is used with that open curly brace, colon, question mark, close curly brace in the string. This can also be derived, which we did in previous episodes as well. And when we talk about derivation, in this case, it's a requirement that these types, like the fields within the type that's being derived, need to be debuggable. But or they need to actually have the same trait, and we'll kind of talk about that in a little bit more detail in a second. But if I actually uncomment this, the not debug is not a debug, or does not implement the debug trait. So if I try to compile, actually, one second, I just gotta fix my usage of it. But if I try to compile with this, you will see that it does not, it cannot be formatted using that kind of placeholder. And it actually tells me I could add derive debug here. So if I go back to my editor, and let's make the not debug actually debug. So now we're okay, we're running, and this prints a nice debug version of that. I think also we showed previously that in addition to print line, there's that little debug macro, which is nice too, because you get that extra information here about the line number and all the fields here. So, but yeah, the main difference is that this debug one kind of gives you this nice summary of all the fields in your struct or whatever object it happens to be. Cool. Okay, so that's debug. Any questions so far? What do you think, Eric?
No, I think you're killing it. I think we'll probably get to it in a little bit, but I definitely think we should show how to look up traits in their implementers, because you had mentioned, for instance, that if something is a display, you can get toString for free or something. So we can show why that is, right?
Some of that was in here. If we actually go, let's just look it up real quick. So Rust display. So if we, I believe it was here.
Right, so this is interesting. This shows you, of course, what the trait is for. It'll show you the declaration of it, what module it's in, and then if you scroll down, right, doesn't it tell you the implementers? Yeah, right. So these are all the types that implement display, which is like a lot of them, right?
Right.
Should be basically all the built-in runs, right?
Pretty much. Yeah, I am trying to, yeah. And I think when we looked at toString,
right.
Let's look at that.
I think this is what you were talking about earlier.
Oh yeah. The tray is automatically implemented for any type which implements display.
Right.
So
and we can see that right there. I think where your mouse is.
And I think when we we're first talking about this, we were looking at the implementers, like why? Oh, there's not that many. But then we looked at display, and there's like tons. And
yeah.
So I was like, why does int have a toString? For example?
it's right there. It says for any t where the t is a display or sized, right?
Right. So now
So that's why we get tons and tons of toString implementations.
Yeah. There you go. So yeah, this basically handles, or this is generating all that code for all the things that implemented display.
Yeah.
Essentially, and size.
Yeah.
That's that. This is kind of something we're not going to go into as much right now, but or does that mean optionally it can implement size? Does that?
I'm not sure.
Right?
I'm not sure, to be honest.
So maybe we'll come back to that in a later episode. But yeah, this is essentially some combination of those two traits. Cool. All right. So back to the common traits. The next one I was going to talk about would be default. Again, this is kind of a nice kind of way to get some shorthand defaults for your structs. It can give you like 0 for numbers, empty for vectors, or empty string for strings. So that way you don't have to like initialize everything when you create your instance of your struct. Can be derived as well. And this is a little different though than what we've seen in these other traits. This is what we call like we said it was associated method, I guess. So this can be called statically. So you just can, if we look down here, I think I'm doing that. Yeah, so I implement this for this point type. Point is just X and Y. And then as you'll see, as I run this, that it gets set to 0, which might be the default anyway, but I mean, we could, so anyway, that is a kind of useful thing for, you don't have to like write as much initialization code. So I wouldn't have to do like X and Y for my point instances. Okay, let's see. Yeah, and then again, here's the derive. So for point, the next trait we'll talk about is from and into. These allow different types to be converted between each other. Pretty self-explanatory and
super useful, right?
Yeah, I would say, somebody told me that it's one of the most used traits in the language. And here we'll see kind of a simple example. Actually, one of the probably more common ones that you'll see is to get a string. Basically, if I have the str string and I want to get a real, this capital string, I can call the from on that and get that capital string. And likewise, I can call the into, which is like the member. So again, just like default, like this is a associated type, so we can call that with a type, and you get your string, which is great. And again, you also get this into whenever you implement the from. So, but just good to know that so that when you need that string or other types, you can what to call. All right, the next one is clone, and pretty easy to implement, I would say. The interesting or the new part here is that
it has to implement this size. Anything that implements clone has to implement the sized trait as well. And that is actually, which we'll get to next, but it's actually something called a marker trait, but that it has nothing to implement. It just means that it has size. So by saying that, you're saying it's a sized thing. But to implement clone, if you had some special cloning logic that you wanted when you copied a value, you could implement that. I don't think did I call it? Yeah, so here I just gave an example with string, which implements clone, and you get the clone string, and then I made this specifically mutable up here so that down here we could like modify it. And if we print out, let's just go back to our fancy directory here. Let's see, and then run. So we'll see that you get those two different, yeah, I think that's right. Let's see. You get those two different strings here. The first one's modified, the second one's not. Okay, moving right along. Got through clone. So the next one is copy. And again, we'll see this kind of, not inheritance, but anything that's copyable should be clonable or should implement clone. And this, is also what we call that marker trait. So that this means that it has nothing for you to implement in it. It's just kind of the compiler can use this to kind of signal what to do when certain operations happen. For example, assignment. So when you copy something, or when you assign something through a copy, if you remember from our ownership talk earlier, this wouldn't have really worked, right? But because we made a copy, there was no what we call that move. So we didn't move values, and so no ownership was changed here, and so this is okay. And Eric, you can print out here, person, and that is copy. And again, here we're using that derive, and see also that we're implementing both because you need to do that in order to implement the other one. The other thing to note is kind of like the debug. We need to have every field inside of it to derive it has to be the same. And I think if I haven't said it already, that's a general kind of principle that when you derive a trait, the subfields or of that type need to be follow that trait as well. So yeah, that is that. I think the next part gets a little more complicated, but it's not too bad. If we want to talk about equality, you might make a custom type and you want it to check if it's equal. This is your trait. It's a little strange, I think. When I first saw it, I was like a little confused. But it's, makes some sense, I think, when you read the docs on this. And basically we're, so we have this equal trait, and then there's saying you have to implement partial equality. So there's some types that I guess when you want to compare them, they're they may be there's no way to, like, I think the example they gave was float, and a float can be if it's not a number, I guess not a number is not equal to not a number. So this gives you both these kind of options. It gives you a default not equal, but yeah, I guess to do the minimum, you have to you could just implement this EQ. And here we're just showing that, like, because this is already implemented by I32, so you can see that's why we can do this sort of thing. And so that's what that enables you to do with your types. And you can see that that's true. Cool. Final note is just a couple of those that we're not going to talk about here, but you will see a bit is our sync and send. Sync and send are for kind of also marker traits. So that means they don't have those methods to implement. And these help the compiler to know like when a type is thread safe so that it's okay to, kind of pass it around between threads. And I think we saw that in the first episode, if you go back there.
Yeah, I think way back in the first episode, actually.
Yeah, I think there was like a few others that we're not covering, but like I think we've talked about a little bit, but there's like iterator. I don't know, Eric, if you have any others you want to mention, but I would say just like go to the docs and you can read about them.
Yeah, so I think that sort of what we showed earlier with the documentation, this is really the bread and butter is if you see a trait, you're not sure what it does, just, go to the Rust docs. It'll tell you, give you a description of it, what methods it gives you, or what methods you need to implement to get it on your type. And then, all the implementers that are already available to you in the standard library. And I think with that, you can really tackle anything. And that's really what this episode is about, I think, is just giving, some comfortability with like what a trait is, how to look it up. They're all over the standard library, of course. Like almost every type in the standard library can be, partial equality'd or, or copied or cloned or whatever. And so it's just important to know where these things come from.
Exactly. Yeah, and I think that's kind of cool because at this point, I think we've covered a lot of the basics that we can use to be kind of do some real work with Rust. So
I completely agree.
Next time we're going to be getting into more building something.
Yeah I think that's well said. No, I think the combination of this making your own data types, ownership and references, if you're already a practicing programmer, like you should have with these episodes enough to sort of get yourself going. Right. And you may not be like 100% effective. You may not know everything, but like, I think that this is enough to start writing programs for sure.
Cool.
All right. Anything else to add before we close out, Noah?
I think the usual, just, hit us up on GitHub or Twitter or whatever.
Yeah.
Your preferred medium. And if you have any questions, leave some more comments.
Yeah. YouTube comments are fine. We love YouTube comments. Cool. All right. Take it easy.
All right. Hey, you too, man. Bye.